Hi everyone. Today I would like to explain about analysis of indeterminate beams using stiffness method. Okay, before we start, I would like to explain about the learning outcome for beam analysis using stiffness method. Number one, at the end of this lesson, you should be able to understand how to identify unconstrained and constrained degree of freedom for beam, how to formulate the element global stiffness matrices, nodal forces as well as nodal displacement, how to solve unknown displacement and reaction, draw, and finally is how to draw the shear force diagram and bending moment diagram for okay. So this is indeterminate beam analysis. Advantage of using stiffness method. So I believe some of you have watched the introduction about stiffness method on how to analyze thrust analysis. Okay, uh, the advantage of stiffness method, we can use we can use stiffness method to analyze statically determinate and indeterminate structures. The method yield the displacement and forces directly. So by comparing to the previous the other method called flexibility method, this is one of the method that can be used to analyze both determinate and indeterminate. And using this method, we can analyze displacement and forces directly. Forces mean reaction at the support as well as internal forces when it is thrust. And when it is beam analysis, so we start with determination of displacement and then reaction at the support, and after that we will continue to draw shear force diagram and bending moment diagram. Okay, the procedure for analysis of beam using stiffness method. Okay, we have to identify member and node. We have to use the global coordinate system, and we have to analyze intermediate loading, and we call this as equivalent nodal forces. And then we will start analysis by identify the stiffness matrix for each element of the beam. Okay, how to do that? So what we need to understand is we have to label coordinate for beam, and then we have to label degree of freedom, and we have to calculate Cx and Cy for each element. And then after that, we have to use the formula. The formula is given. Okay, you can find in appendix. So it is 4 by 4 matrix because there are 2 degree of freedom per node, and one element consists of 2 nodes. One element consists of 2 nodes. So we will produce the element stiffness matrices. So from element stiffness matrices, we will combine to have the structure stiffness matrix. The symbol is capital K, which represent all nodes. Okay, from that, we will apply what we call as stiffness equation. Stiffness equation is actually come from force displacement principle, where we have to define the nodal forces, nodal displacement, as well as equivalent nodal forces before we write it all into what we call as stiffness equation. And from that, we will cancel all zero displacement when we apply the boundary condition. So we will have normally we will analyze displacement using by or considering unconstrained system only. So these are the formula to calculate the element stiffness matrix or the member stiffness matrix. It is 4 by 4. So the formula is like this. 4 means there are two DOF at near end node and another 2 DOF at far end node. Okay, so the most important thing whenever we determine the element stiffness metric is how we label the degree of freedom, because labeling must be done correctly in order to produce the right structure stiffness matrix. So let's look at the example here. So this is one indeterminate beam example, consists of two element or two members, member AB and member BC. And this the member AB is loaded with UDL, and member BC is subjected to point load at the center of member BC. There are actually one fixed, one roller, two rollers. So there are five unknown reaction if we look at this conventionally. However, when we analyze this using stiffness method, we have to analyze this based on stiffness matrix principle, where we have to count the degree of freedom per node. And in beam analysis, we have to consider two DOF per node in Y and Z direction only. We don't have to count X, because X there is no horizontal force, there is no horizontal displacement in beam. Okay, so this is the first step. Actually, the first step is we have to label the degree of freedom. Normally, we label the degree of freedom. We have to differentiate between unconstrained and constrained system. Unconstrained where displacement occur, and constrained where reaction occur. So we have to define because we have to label the degree of freedom in unconstrained system first, and then we followed by labeling the DOF in constrained system. Because in unconstrained system, where we need to calculate the unknown displacement, and unknown displacement is the first output. Using the displacement that we calculate, that only we will calculate the unknown reaction. Okay, so this is the element stiffness matrix. There are two elements, K1. Member AB is considered as K1. Member BC is considered as element number 2. So there are 4 by 4 matrix. So the label that we can see here, labeling by the red the red color font, so representing the degree of freedom. So we have to label it correctly, where we have to label near near xy, far xy. 3 is near x, 4 is near y, near y. So near xy, far xy. So that is why we get 3 4 5 1. Means that 3 4 belong to near n, 5 1 belong to far n. And 3 4 means x, not xy. 3 4 means yz, and 5 1 means yz in far n. Okay, the value inside the matrix is just we follow the formula given in appendix. Okay, so this is the stiffness matrix, the element stiffness matrix for member BC or element number 2. Okay, again, the value inside the bracket is actually we get from calculator. We get from formula. We just calculate it using calculator. However, what most important is the degree of freedom that we label. The degree of freedom that we label 5162. 51 means near n, 62 means far n. 51 means near n, 62 means far n. So 51 means yz. Y5 Z is 1. 5162 means 51 means near YZ, far YZ. Okay, then we have to combine from K1 and K2. We have to plus these two, K1 plus K2, and K1 plus K2 equivalent to capital K. Capital K, the degree of freedom is 6 by 6, since there are three nodes A, B, C just now. So 3 means 3 times 2. So in total there are 6 degree of freedom. So we produce 6 by 6 matrix for the structure stiffness matrix. And for the structure stiffness matrix, we have to write it in order. We don't have to define where it's near, where it's far. We have to label it in order. So the number that we that we label under the element stiffness matrices, we actually the number representing the position. So what we should do now is we have to plus all the same position. Means that for 1 1 we have to plus this 1 1. Means that this 1 1 we have to plus with this 1 1, so we get this 1.777. Okay, we have to plus based on the position. For example, we want to find the value of 1 5. So 1 5, we have to find 1 5. Where is 1 5? This is 1 5. 5 1 is the same. and then we have to plus with 5115 is the same, so it is negative 0.074. We have to plus with 0.667, and then we get this value 0.593. So we do to all position, and finally we get all 6 by 6 stiffness matrix. Okay, so after that, we have to establish what we call as nodal displacement and nodal forces. For nodal forces Q, so we will write in matrix from 1 to 6 position, Q1 until Q6, and we do the same for the unknown displacement, nodal displacement from D1 until D6. However, at this stage, we have to consider the value which is given in the question, and the value, for example, at position number 1 and number 2, which representing moment. So there is no applied moment at B, there is no applied moment at C. That is why the value is 0, because 1 and 2 representing Z rotation. Z for Q is representing moment. So if look at the diagram, if is there an applied moment that is subjected into the system, there is no moment found, so the value is 0. Okay, the rest from for position 3, 4, 5, 6, so we have to remain as symbol, because that is the second output, the reaction at the support that we are going to determine later on. Okay, for displacement, so displacement D1, D2, we have to label as symbol, because D1 and D2 is the first output that we are going to determine by solving stiffness equation, and D3 until D6, D3 until D6 is actually the displacement at support. And since at support we understand that there is no displacement, that is why we have to label by 0. Okay, we have to label this by 0. Okay. Okay, next step is, since this beam is subjected to UDL and point load, which is located on the member or along the member, we have to distribute it to nodes. Remember, Q, nodal forces, is just for forces that is subjected directly at nodes. However, whenever the member has been subjected to forces on the member, so uh, we have to distribute it equivalently. So we call it as equivalent nodal forces. So we calculate using the fixed end moment formula, and then we get like this. Okay, and again we have to refer back to the label that we have made for K1 and K2 to label Q1 node and Q2 node. We total all this and we get equivalent nodal forces, a 6 value, Q naught. So all this we substitute into what we call a stiffness equation. Stiffness equation, Q is equal to KD plus Q naught, and whenever we want to solve for the unknown displacement, we just need to consider this portion only. Okay, we just need to consider this portion only. It is due to unconstrained degree of freedom. So we just need to actually solve two simultaneous equation. Okay, solve two simultaneous equation, then we get displacement D1 and D2. So from D1 and D2 value, we just need to substitute back into the stiffness equation, and we solve for remaining. We solve for Q3, Q4, Q5, Q6. Okay, using matrix multiplication, we put the D1 and D2, okay, into the stiffness equation at D1 and D2 position, and we continue by using matrix multiplication to calculate the reaction at the support. Okay, so all this we plot back into the diagram, and we get all the reaction at the support, and from that we can draw the shear force diagram and the bending moment diagram, and it is look like this. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.